Welcome to my video course on principles of railway control and communication systems. You know, trains are incredibly heavy, insanely fast machines that fundamentally just cannot steer. They're locked onto fixed tracks, which means they can't simply swerve out of the way to avoid a collision like a car can. Because of that reality, we need absolute, flawless control to keep everything safe. Think about it. We're talking about thousands of tons of metal hurtling along at high speeds, so the margin for error is effectively zero.
In today's explainer, we're going to build a comprehensive understanding of railway operations by exploring 5 foundational modules: the 4 signaling principles, safe train separation methods, modern train control systems, the role of telecommunications, and finally, traffic management and operations. Let's jump right in.
Module 1, the 4 signaling principles. To maintain our ultimate goal of safety, absolutely every signaling system on Earth is built on these. There are 4 golden rules here. First up is safe spacing. We've got to guarantee a train is given a route completely clear of any other traffic. Second, no excess speed, meaning the train has to operate within the specific speed limits for that given route. Third is route holding. This one is crucial. Once we give a train a route, we can never revoke or alter it without absolute assurance the train won't actually use it. And fourth, no conflicting moves. The route we offer a train can never cross paths dangerously with a route offered to another train. Together, these 4 principles guarantee that whether we're doing high-speed mainline running or just low-speed shunting in a depot, trains stay safely spaced.
Now, equipment fails, right? That's just a fact of engineering. But when designing these railway systems, we have to ensure they fail safely. If a signal loses power, it should automatically drop to red to stop all traffic. What we absolutely have to avoid at all costs is a wrong side failure. This is basically a nightmare scenario where a malfunction actually removes our vital safety protections, like a broken signal falsely showing a green light when there's actually a train sitting just ahead. Pretty much everything we design in this industry is built specifically to prevent a wrong side failure.
Moving right along to Module 2, safe train separation methods. Now that we've got the core rules down, let's look at the actual physical methods we use out on the tracks. Historically, how we keep these massive trains apart has gone through quite an evolution. In the very early days, we relied on primitive visual on-site operations, where the driver quite literally just looked out the window. Then we tried simple time intervals, like, okay, let's let a train go 5 minutes after the previous one. But as speeds increased, we had to move to absolute block working and track circuit block working, which divide the physical track into fixed, rigid sections. Fast forward to today, and we are rapidly shifting toward highly complex, automated moving block systems. This shift is really a game changer, and here's why. With fixed blocks, you're relying on rigid sections of track. Only one train is allowed in a block at a time, which leaves a ton of wasted, empty space trailing behind a train. But with moving blocks, it creates this dynamic, invisible safety bubble that wraps right around the train, constantly recalculating based on its exact real-time speed and braking distance. If a train slows down, its required braking distance shrinks, meaning the train behind it can safely pull up much closer. We're talking about a massive increase in the overall capacity of the line without sacrificing a single ounce of safety.
That brings us perfectly to Module 3, modern train control systems. To achieve that advanced moving block separation, we rely on some seriously heavy-duty computing.
A prime example of this is the European Train Control System, or ETCS. Historically, every country built its own bespoke signaling system. Imagine driving your car across Europe and having to swap out your engine, or even your driver, at every single border, because the computers literally couldn't talk to each other. Well, ETCS was designed as a standardized, interoperable suite to eliminate that massive headache for trains. ETCS actually scales up in complexity. Level 1 acts as an overlay on top of traditional physical signals by the track. Level 2 steps it up by using continuous radio communication, which makes those physical line-side signals completely obsolete. But Level 3? That is the holy grail. By Level 3, we completely ditch conventional track detectors. We rely entirely on the train constantly reporting its own exact position and continuously confirming it hasn't accidentally uncoupled any railcars. That's how we maintain those invisible moving block bubbles we were just talking about.
Now, while ETCS was essentially born for the mainline, for mass transit subways and metros, we use something called Communications-Based Train Control, or CBTC. It offers those same incredible moving block advantages, but it heavily focuses on taking vital equipment off the side of the tracks and putting it directly into the train's onboard computers.
For CBTC to work flawlessly, it demands incredibly robust train integrity monitoring and totally reliable non-stop communication.
Which brings us to Module 4, the role of telecommunications. None of these modern train control systems work without a rock-solid digital nervous system.
This telecom's nervous system has a few major jobs. Yes, it facilitates standard voice communication between the train driver and the control center. And of course, it's vital for hazard reporting or coordinating accident response teams. But the absolute critical piece here is that telecommunications networks act as the bearer service for the signaling data itself. The digital data that is actually holding these thousands of tons of metal apart, authorizing them to move safely, is traveling continuously over these exact radio and data networks.
And we need to be clear, there is a stark, night and day contrast between the network your smartphone uses and the one the railway relies on. On a public telecom network, if you drop a call in a tunnel, it's an annoyance. But on an operational railway network, a drop connection means a train literally loses its movement authority and the whole line comes to a screeching halt. Railway telecoms have to survive incredibly harsh environments, extreme physical vibration, massive electromagnetic interference from high-voltage power lines, and they absolutely require guaranteed, continuous, 100% route coverage, zero exceptions.
Finally, Module 5, Traffic Management and Operations. Let's zoom out and look at the big picture. So we've got our signals enforcing the rules, our moving blocks keeping trains dynamically spaced, and heavy-duty telecoms keeping everything perfectly synced. The railway runs on a super strict daily timetable. But here is the multi-million-dollar question. What happens when the timetable fails? What happens when a train breaks down or there's severe weather? The rigid, static daily plan instantly falls apart, and that is exactly why dynamic traffic management is an absolute necessity.
To handle this, we use systems like automatic route setting, or ARS. Traditionally, ARS only knew the static morning plan, but modern traffic management systems are wildly smarter. They identify conflicts well in advance, say predicting that two trains are going to fight over the same junction 20 miles ahead. They automatically update the ARS with a brand new dynamic timetable, routing trains in real time and keeping the whole network flowing smoothly without controllers having to frantically intervene. But, and this is a big but, despite all this incredible automation, we cannot just remove the human element. The train controller is the person sitting in the control center who is ultimately responsible for the safety of their section. When things go truly wrong during degraded operations or major emergencies, the human train controller retains the ultimate authority. They can step right in, switch off the automatic route setting, and manually route those trains to guarantee absolute safety.
Still, as technology just keeps marching forward and intelligent traffic management systems demand ever more precise, real-time data capable of analyzing millions of variables a second, you really have to wonder how the role of the human operator is going to evolve next. Will we always need a human in the loop, or is full AI automation the inevitable destination? It's a fascinating question, and thanks. We'll see you next video.